Hi, and thanks for joining. Today we'll be discussing the continuous non-invasive hemodynamics monitoring system for humans, otherwise known as the Nano. That might have sounded like a bit of a mouthful, so to break it down into layman's terms, essentially what this is a continuous beat-to-beat blood pressure signal that's achieved non-invasively, meaning without any needles or invasive procedures. By the end of today's video, I'm hoping that you'll feel confident in your understanding of the technology and theory behind the Nano, and I'm also hoping that you'll have a thorough understanding of the hardware and software involved in the system. So what exactly is the Nano and what does it offer? It's a great question and a great place to start. As I mentioned, it's a beat-to-beat blood pressure monitoring system. And what's important to note about that is with a beat-to-beat continuous blood pressure waveform, you're not going to miss any sort of signals or events or markers that you might miss if you're using something like a traditional brachial cuff that's more so a moment in time recording rather than a comprehensive waveform. It's a non-invasive solution for hemodynamic evaluation, and it was really expertly engineered with patient comfort in mind. In addition to it being non-invasive to improve patient comfort, it comes with flexible finger cuffs and a comfortable wrist unit that are easy to wear. It's really revolutionized hemodynamic data collection across the board as being a reliable, powerful, and easy-to-use tool that can be implemented across a variety of fields, including autonomics, exercise physiology, cardiology, and in recent years, lots of COVID research. Although this is primarily a science video, we're going to take a quick step back for a history lesson of Finapres and ADI. So the Nano is really a product that's been developed over 30 years based on research and user experiences. You can see in the timeline below that there have been quite a few iterations of non-invasive blood pressure devices developed with Finapres technology. And I think that really speaks to how fine-tuned this device and system has become over the years. ADI sold Finapres for over 20 years before becoming the Nova's exclusive distributor in the United States in 2020 and becoming the Nano's exclusive distributor worldwide. Some of you may have already heard of the Nova, which is sort of like the sister product to the Nano. So I wanted to put the two side by side so we can really compare and contrast the features of each. So the Nano is a really great tool for research. It's compact with a small footprint, which is great for labs, and it streams directly into LabChart as a LabChart compatible device. You can also use a free LabChart extension called NICO to determine cardiac output, stroke volume, and total peripheral resistance. The Nova is something that can be used clinically to treat and diagnose patients, as well as in the research space. It has a monitor, like you can see in the bottom right-hand corner, to view data, and you can use it with a data acquisition system, like a Power Lab, to output signals to LabChart if needed. To calculate those cardiac output, stroke volume, and TPR signals, instead of using LabChart and NICO, you could use something called Advanced Hemodynamics, which is based on the model flow algorithm developed by Finapres, and this would be a paid software extension. The two have quite a few similarities as well. Both are going to utilize the gold standard, trusted, and validated volume clamping method. They can both be used in dual cuff mode, which is especially nice for longer recordings. They use the same exact nanocore wrist unit, which houses much of the proprietary technology. They both utilize a height correction unit to account for hydrostatic pressure change between the heart and the hand. And overall, with either choice, you can rest assured that you're getting the industry-leading accuracy and blood pressure. I wanted to chat a little bit about validations and accuracy. As scientists, you know just how important it is to have accurate, validated data that you know you can trust. You don't want to be jumping to conclusions or making publications without being confident that what you're recording is an accurate representation of what's going on physiologically. As you guys know from our little history lesson, this technology's been around for decades. First debuted in 1973 when Dr. Peñas published photoelectric measurement of blood pressure, volume, and flow in the finger. And since then, there have been dozens of publications that attest to the accuracy of the technology. Many of the publications validate the non-invasive blood pressure using a finger cuff as compared to more traditional methods like an arterial line or thermodilution. So you can rest assured that it's going to be very accurate, especially when compared to more traditional invasive methods. All right, now to dig into the nitty-gritty of the technology behind the system, we first need to discuss the volume clamping method. And this was what was introduced by our friend Dr. Peñas in the last slide in that 1973 publication. Essentially, he demonstrated that continuous non-invasive blood pressure can be recorded with finger arterial pressure by using a finger cuff. And he proposed those cuffs house an inflatable bladder and plethysmograph, which would incorporate a light source, LED, and detector. How this all comes into play is light is absorbed by the blood, and then the pulsation of arterial diameter during a heartbeat causes a pulsation in the light detector signal, like you can see in the diagram below. A really key feature of both the Nano and the Nova is going to be called Physiocal, which is the calibration algorithm built into both systems. It prevents drift in the measured finger pressure due to arterial contractions and relaxations, which would be related to smooth muscle activity in those finger arteries. It also defines and maintains the correct diameter or set point at which the finger artery is clamped. So this means your cuffs are never going to be too tight, and therefore not result in anything like a purple finger or purple arm like you see on the right. Overall, this is going to ensure signal quality and accuracy so you can be confident in the data that you are recording. The Physiocal calibration feature is complex and thorough, so I've broken it down into a couple of steps to make it a little easier to understand exactly what's going on during this process. The first step is going to be assessment, and this is when light sensors assess the finger arteries to determine the unloaded state. And remember, those light sensors are going to be inside of the cuff. Next is going to be adjustment, and this is when feedback from the cuff dynamically adjusts cuff pressure to keep the diameter of the arteries unchanged. Lastly is acquisition, and this is when the final calibrated blood pressure signal is acquired and displayed in LabChart. At this point, pressure inside of the cuff needed to maintain equilibrium is representative of arterial blood pressure in the finger. All right, so we've covered science and history. Now it's time for a math lesson. Sort of like the cartoon in the bottom, we're going to break this down a little bit further so that you understand exactly what's going on in fine detail. So NICO, as I've mentioned previously, is a free LabChart extension that will allow you to calculate parameters like cardiac output, stroke volume, and total peripheral resistance. The extension supports 2 different methods for estimating cardiac output for you to choose from. The first is going to be the Windkessel 3-element model, and then the other is going to be the Liljestrand and Zander nonlinear compliance. We're going to start with Liljestrand as it's the simpler of the two. It essentially assumes that cardiac output is proportional to the difference between the systolic and diastolic pressure divided by the sum of the systolic and diastolic pressure for each beat, and it does not take into account factors like age or sex. You can see the reference for the formal paper below if you'd like to read up on it in more depth or brush up on your German perhaps. And I have an example of the equation listed below with some of those variables to find. As a reminder, you don't need to formally understand the Liljestrand or Windkessel model to be able to utilize these features. This just gives you a bit of background of what's actually going on in the software to calculate these parameters using NICO. Next, we have the Windkessel model, which is truly a slice of genius while also being a bit of a bear. So we won't get into it in too much detail. I'll just give you enough information for you to understand on a surface level what's going on. So the technical definition of this method is that it uses blood pressure measurements to solve a varying nonlinear differential equation which corresponds to a Windkessel 3-element model of aortic input impedance. Now bear with me, we're going to break that down a little bit into something that's a little bit easier to grapple with. Essentially what that is a multi-step or multi-stage calculation that allows you to calculate parameters like cardiac output, stroke volume, and total peripheral resistance, using the factors that you see in the diagram and in the key on the right-hand side. There are 3 overarching steps to the Windkessel model, which are outlined at the very bottom. First, numeric values for Z0, CW, and RP must be calculated in order to calculate instantaneous flow. After that, instantaneous flow is then integrated to determine stroke volume. The last step is cardiac output is then calculated by applying stroke volume with instantaneous heart rate, which is derived from the pressure signal. The last thing I have on the docket for us to cover is going to be system components. We'll work around the diagram in a counterclockwise fashion and discuss each item that would be included in the system. First, we'll have the human hNIBP nano interface. This is what's considered a LabChart compatible device, meaning it can connect directly to your computer and stream data directly into LabChart. Next, we have the nano core wrist unit, which would connect to the front of the Nano interface. This would be the same wrist unit as you would have with the Nova. Connected to the wrist unit, we have finger cuffs. Those finger cuffs are reusable, so you can get plenty of uses out of them before they ever need to be replaced, which is both environmentally friendly and easier on the researcher and lab to not have to constantly reorder cuffs. Lastly, we have the height correction unit. This little geyser is an important feature of accounting for hydrostatic pressure changes between heart level and hand level. This means you don't have to hold your hand at heart level throughout a recording, which is especially important in studies like an exercise physiology study or a sleep study. To give you an idea of what this data would look like once streaming into LabChart, here's a quick recording of a sample file. Thanks again for joining, and if you have further questions, please feel free to contact ADI using the Contact Us tab on the webpage or by calling the number on the screen.